A very important example of reactions involving reactive intermediates is polymerization. One of the main chemistries for making polymers is free radical or chain growth polymerization. Polymers like polyethylene, polystyrene, polyvinyl chloride, and many others are made through this mechanism. The other common class of polymerization reactions is condensation polymerization, which forms the materials like nylon. The general steps in chain growth polymerization are initiation, propagation, and termination. Initiation usually involves reaction of a monomer with a radical. This kicks off the polymerization process. The radical is formed from decomposition of some initiator that's added to the reaction mixture. So let's look at this process for a monomer like ethylene. So our first step is initiation, where we have some initiator, we'll label here I, decomposing to form two radical species. We then have a reaction of one of these radical species with a monomer. So for example, this could be a radical reacting with our monomer here, ethylene. And so these vinyl type species where we have unsaturated CC bonds are very reactive with radicals. And so if we do that, essentially now can have the radical added to our ethylene to form this radical monomer species. So this is now able to react with other ethylene monomers and kick off the polymerization process. So the next step of polymerization is propagation. So here we have reaction of that radical species, which we formed in the initiation step, with a monomer. So the result of this propagation step is now we essentially transfer that radical to the end of this now starting to grow chain. So now we have two monomers linked together, still with this radical species, where now we can add additional monomers to the end of this growing chain. So with each additional monomer added during propagation steps, and so we can have very many of these, the polymer grows in length. And monomers are only added at the end of this growing polymer chain. So our final step will be a termination step. So if we have now our polymer of some length, that still has this radical end group, it can react with some other radical species. So in this case, I'll just write it as some other polymer fragment. And this could be a different length. So when these two radicals combined, they essentially quench each other to form this stable polymer species. So at this point, this polymerization reaction is finished. And I'll just note here that typically we leave the initiator off since the chains are long, and so the initiator R has little impact on the final material properties. So let's think a little bit about this chain growth polymerization process and the kinetics involved. So we can represent this. We'll write each one of the different steps, starting with initiation. And so we'll write the initiation process as an elementary reaction. It's the decomposition of this initiator with a rate constant Kd for decomposition. So also in this initiation process, one of these radicals will react with a monomer, which will denote M, to form one of these growing chains, and so the subscript here notes the size or number of monomers involved. And so we'll give this a rate constant Ki for the initiation. Following initiation, we can have propagation steps. And so we'll write M1 this radical species is able to react with a monomer with some propagation rate constant, which we'll call Kp1 for a monomer or a polymer, growing polymer of length 1. And so this will form be addition of that monomer. So now we'll form a radical species M2 dot. So this radical species can, of course, also add another monomer. So we can have another propagation step to form a slightly longer polymer chain. And so we'll have, many of these types of propagation steps where we'll just give an arbitrary number, mn, plus the addition of a monomer here. We'll give that a propagation rate constant Kpn to form a polymer of length n plus 1 number of repeat units. So in general, we'll say that the propagation rate constants for any one of these steps are equal, as these are all very similar chemical steps. So essentially in this case, we have all additions of a vinyl type monomer to a chain by a radical. And then finally, we can write our termination steps. So this could be reaction of one of these growing radical chains with another one. So there are a few different ways this could happen. So we could have termination by combination. So these two essentially add together to form a monomer of length, say n plus m in this case, if the two radical species were of lengths n and m. Or we could have what is called disproportionation. And so this will give us two polymers that are both stable, but of different lengths. So we can write the rate of polymerization as the rate of disappearance of monomers. So we'll say the overall rate of interest, is equal to the negative of the derivative of monomer concentration with respect to time. So monomer is consumed in two different ways. So we consume monomer in the initiation reaction, where we react this radical R dot, it's formed from our initiator, with monomer to kick off the polymerization process. And then each one of our propagation steps involves consumption of a monomer. And so these propagation steps will depend on the propagation rate constant, which we assumed was the same for any one of our propagation steps, the concentration of monomer, and then the concentration of growing chains. So here we can keep track of these by doing a summation over these growing chains of any length I. Or we can write this a little more simply by lumping these together. So everything will look the same here, except now we'll replace the concentration of growing chains with just m dot. Okay, so now we have this rate expression for the rate of polymerization, but we have two quantities which we cannot easily measure. So the concentration of radicals that initiate the polymerization process, R dot, and the concentration of growing chains, m dot. So we can apply the pseudo-steady state approximation on each one of these species to get rid of these non-measurable quantities in our rate expression. So here these radical species are going to be very short-lived. So we can write that the rate of reactions that produce these radical species are equal to the rate of reactions that consume them. So for R dot, we can do this by equating the rate of formation of that species. So this is the rate of decomposition of our initiator. So 2 kd times the concentration of initiator is equal to the rate of initiation of the polymerization. So that's the rate of R dot reacting with our monomer to kick off the polymerization process. So here we can rearrange this expression solving for R dot. So this is now all in terms of measurable quantities, 2 rate constants for initiator decomposition and initiation of the polymerization process, and concentration of initiator and monomer, which we easily measure when we sort of load initiator and monomer into our reactor. So similarly, we can do a pseudo-steady state approximation on m dot. And so what this would mean is that the rate of initiation and the rate of termination are going to be equal. So we can write the rate of initiation, so that would be Ki times R dot times M is equal to, so we have 2 termination pathways. We could do combination termination or disproportionation, and this will depend on our concentration of growing chains squared. So substituting our expression for R dot, so this expression here, into our expression, our pseudo steady state approximation for m dot, we can write that 2 times Kd times Ki times the initiator concentration is equal to the rate of termination. So this is 2 times the rate constants for combination and disproportionation termination times the concentration of growing chains squared. So now we can solve for our concentration of growing chains, and this comes out to an expression that looks like this. So it depends on our initiator concentration, the decomposition rate constant, and our 2 types of termination rate constants, all raised to the 1/2. Okay, so now we have expressions. What we really wanted to do, going back to our rate equation, was here replace the concentration of radical species R and growing chains M with measurable quantities. We now have them from the pseudo steady state approximation, first on R dot and secondly on M dot. And so now we can use those expressions to come up with a rate equation for the rate of polymerization just in terms of measurable quantities. So if we do that, plugging everything in, we can write that the rate of polymerization is equal to 2 times the rate constant for decomposition of our initiator times its concentration, plus the propagation rate constant times the concentration of monomer, times essentially what was our m dot, okay. So here we've arrived at a rate expression that gives us the rate of polymerization, all in terms of measurable quantities, starting with a sequence of elementary steps for this chain growth polymerization. So many of polymers' properties are influenced by their molecular weights or number of repeating units. So this includes thermal properties like the glass transition temperatures, mechanical properties like stiffness and toughness, and flow properties like viscosity. So understanding polymerization kinetics can actually help us to characterize polymer size or molecular weight. So one parameter used to characterize the size of polymers is the degree of polymerization. So this is equal to the number of repeat units in the average polymer chain and is related to the number average molecular weight like this. So we can write that the molecular weight, the number average, is equal to the degree of polymerization, so how many repeat units we have in each chain, times the molecular weight of that repeat unit. So the degree of polymerization we can calculate as the rate of propagation divided by the rate of initiation. And again, if we have a pseudo-steady state approximation on our growing chains, the rate of initiation and the rate of termination are going to be equal. So we can write this as the rate of propagation. So that's going to be the propagation rate constant times the concentration of monomer times the concentration of growing chains, divided by, here I'll write, like I said, the rate of termination and initiation are equal. So I'll write the denominator here as the rate of termination. So this depends on our rate constants for our two mechanisms of termination times the concentration of growing chains squared. So this will simplify to the propagation rate constant times the concentration of monomer over our rate constants for termination times the concentration of growing chains. So note this is closely related to another common term known as the kinetic chain length. So the kinetic chain length, we denote V, and it's going to be equal to the propagation rate constant times the concentration of monomer. So here the only difference in terms is the coefficients on our termination rate constants. And so we can write the degree of polymerization in terms of measurable quantities using the expression for the concentration of growing chains from the pseudo-steady state approximation. So if we do that, this gives an expression that looks like this. So if we assume, for example, that the combination termination is dominant, we could write the degree of polymerization here as the propagation rate constant times the concentration of monomer divided by the termination rate constant to the 1/2 times the decomposition rate constant times the concentration of initiator. So we can see essentially that the length of our polymer chains is going to depend on how relatively fast propagation is relative to termination. So how long the polymer continues growing before that radical is quenched and polymerization is finished. It also depends on our concentration of monomer and is inversely related to our amount of initiator. So this showed how we can understand rates of polymerization processes using pseudo-steady state approximation and starting from a sequence of elementary steps. And so again, from this, we can do things like characterize the length of these polymer chains, which gives rise to important materials properties.